So hi all. So I am Shubhajit Das, one of the TAs for this course, and welcome to week 2. So as we do every week, we will solve some problems, and these problems, as I said last week, are actually based on your assignments, whatever you have learned this week, and some are my own input usually. So first of all, can you guys see my screen? Can you just reply in the chat? Okay, thank you. So yeah, so let's start. So we start off with a very simple problem or a simple question, which is about finding the number of automorphisms of Zn under addition. You know that Zn is a group under addition. So you are asked to find out all automorphisms of Zn or all symmetries of Zn. So first of all, are you aware of what automorphism of a group means? You can just reply in the chat. You know what group homomorphisms are, right? So do you know what automorphisms are? Can someone reply? I mean, you probably have studied, right, what automorphisms are? So in case you don't know, let me just then recall it, what automorphisms of a group actually mean. So basically you take a group, okay, so you take a group, let's say G. So you know what if G and H are groups, you know what a homomorphism from G to H means, right? That you know. So you also know what an isomorphism of group means, right? It's just a bijective homomorphism, right? So if you take an arrow of groups or a morphism of groups which is bijective, then you call it an isomorphism of groups. Now an automorphism of groups is an isomorphism whose domain and codomain are the same. So if G is a group, then an automorphism of G is just an isomorphism of G onto itself, right? It's as simple as that. So this is what an automorphism of a group means, or automorphism of a group is. So you are asked to find the number of automorphisms of Zn under addition. So any ideas? Anyone wants to answer this probably? I mean, you can just unmute yourselves as well if you want. Instead, if you don't want to write on the chat, you can just unmute and let me know. So do you have any ideas what how many automorphisms Zn has? I am audible, right? Okay, so fine. So we just quickly provide an answer to this problem. So you know what automorphisms are. So automorphisms are isomorphisms of a group onto itself, that is mappings of a group, bijective mappings of a group onto itself, which also map the structure identically onto itself, right? That is what it is. In other words, it's kind of an abstract symmetry of a group, right? So if you consider Zn under addition, and if you take an automorphism of Zn, you know that Zn under addition is a cyclic group, right? This is a cyclic group, right? And you know that the element 1, that is a class of 1, generates this cyclic group, right? That you know. So if Zn under addition is the cyclic group generated by 1, and if you take an automorphism of this group, then an automorphism which is in particular an isomorphism should preserve the order of the elements, right? So if you take phi to be an automorphism of Zn under addition, then whatever order A has, so we know that phi is an automorphism. So phi preserves order of elements, right? So in particular, since 1 has order n, so we know that phi of 1, phi of the class of 1 has order n. In other words, what I am trying to say is, if one is a, since 1 is a generator of Zn under addition, you definitely know that its image will also be a generator of Zn under addition, right? Right? So you can see my screen, right? I don't know why the writing has stopped. First of all, am I audible? Can someone just reply in the chat? Screen stuck. Okay. Oh, I think. Okay. Yeah. So maybe now. Right. Okay. So yeah. So we know that yeah. So what I was saying is that phi is an automorphism of Zn under addition, and therefore phi must preserve the order of all elements. In particular, if you take a generator of Zn under addition, which is an element of order n, then its image under this mapping should also be a generator of Zn, right? That is, it should also have order n, right? So we know that phi of 1 has order n, right? And since Zn under addition is cyclic, you know that the entire map phi, which is defined from Zn to Zn, is actually determined by where it takes the generator 1, right? If you know where it takes 1, since it's a homomorphism in particular, you know the mapping on the entire Zn, right? So it can be uniquely, it can be uniquely extended to all of Zn. I mean, not exactly uniquely, but yeah, its image, the image of 1 fully determines what the map will be. That is what I'm saying. So the entire map phi is fully determined by where it takes 1, right? That you know. So so what you know, so basically what I'm trying to say is, if you want to find the number of automorphisms of Zn under addition, then that is at most the number of generators of Zn, right? Because every generator of Zn gives you a particular automorphism, right? So these are the key points. If A is a generator of Zn, then there is an automorphism which sends 1 onto A, right? This is what it is. If A is a generator of Zn, then you will find an automorphism which sends 1 onto A, right? So what is that automorphism? So basically, maybe let's say the automorphism is phi A. So what does phi A do? Phi A sends 1 onto A, and we define phi A like this. So phi A of class of K is obviously what it should be, K times A, right? For all class of K in Zn, right? So you can check that this is a well-defined mapping, and this indeed is bijective and is an automorphism, right? It maps the generator 1 onto the generator A, right? So every generator of Zn gives you an automorphism of Zn, right? And how many generators does a cyclic group have? That you know clearly, right? So there is, I should write something more, there is a unique automorphism, yeah. Since Zn under addition has phi n generators, where phi, by the way, is Euler's phi function. Okay, so let me use a different notation for this one. Phi n generators, hence there are phi n automorphisms. of Zn. And it's as simple as that. You know that a cyclic group has phi n generators. So yeah, it's as simple as that. Phi n, by the way, as you know, is Euler's phi function, right? That is, for any positive integer n, it is a number of integers greater than equal to 1, smaller than n, and which are relatively prime to n, right? So yeah, so the answer to this question will be precisely phi of n, right? The number of automorphisms of Zn under addition will be phi of n, right? So do you have any questions? Do you have any? If you have any question, that you can ask me in the chat. Okay. I mean, it would be better if you were a bit more interactive, because I won't understand, no, unless you say if there's a problem or not. You can maybe unmute your mic and say me also. That's also an option. I don't have a problem with that. So anyways, so we come to the next question. So you know what automorphisms are, and we clearly have found out that the number of automorphisms of Zn under addition is precisely phi n, right? So Zn under addition has phi n many automorphisms, yeah. And you know that the automorphisms of any object, let alone a group, the automorphisms of any object themselves form a group, right? So let's say if you have you guys studied metric spaces as of yet in mathematics? Can someone reply? Okay, good. So you have studied metric spaces, and you know what are the right kind of maps from one metric space to another, right? That is, the maps between metric spaces are isometries, right? Not matrices, I am talking about metric spaces. A set together with a distance function defined on it. That is what I am talking about. So, okay, fine. Let's forget metric spaces. Let's forget that. What I am trying to say is, in mathematics, whenever you will study any kind of object, so suppose this is a kind of object. I am denoting by a blob or dot, but suppose this is some object. It might be a group, it might be a ring, it might be a field, it might be a metric space, it might be a topological space. Any kind of mathematical object, whenever you study, you also study the notion of a structure preserving map from one object to a like object, right? And here also you can talk about isomorphisms and you can talk about automorphisms, right? Which are isomorphisms of this object onto itself, right? So you can check that the automorphisms of any mathematical object always form a group, right? So if you are talking about automorphisms of, let's say, a group, they form a group. If you are talking about automorphisms of a, let's say, ring, that will also form a group. If you are talking about automorphisms of a set, that is bijective maps of a set onto itself, they clearly form a group, as you know, right? That's called the symmetric group. So whenever you take automorphisms, whatever the structure is and whatever be the right notion of a structure preserving map and hence an automorphism be, the point is that the automorphisms of that object will always form a group, right? Now for our case, we are currently talking about groups, right? So we are talking, for our case, the mathematical object that we are interested in is groups, and we are interested in finding the automorphism group of known groups, right? You know that the automorphisms of any group form a group, right? Under composition, obviously. So yeah, so we want to find out what is this, or in other words, we want to show that the automorphism group of Zn under addition is Zn star, right? You know what Zn star is. It precisely consists of all elements of Zn whose representatives are relatively prime to n, right? That is what Zn star is, and it is clearly it is also a group under multiplication. So these are known groups for you. We just want to prove that automorphisms of Zn are this group is isomorphic to Zn star, right? So just recall what we have calculated just above. So we calculated that cardinality of aught Zn, that is the number of automorphisms of Zn under addition, is phi n. This is what we, okay, so this is what we obtained just a few minutes back. right? And we also know that Zn under Zn star, this consists of all representatives of Zn, consists of all classes of Zn whose representatives are relatively prime to n. That is, Zn star also has phi n many elements, right? So if you want to find an isomorphism from odd Zn to Zn star, you know that first of all they must be in bijective correspondence with each other, and clearly both of them have cardinalities phi of n, right? So we understand that there can be an isomorphism from odd Zn to Zn star, and indeed there is. So I'll just leave the map, I'll just write down the map, and I'll leave for you to check that this is in particular homomorphism and all that. Okay, so define so let me use a different notation for a map. Psi from odd Zn into Zn star. So what we do is, odd Zn is the group of all automorphisms of Zn. So in particular, an element of odd Zn is a map f, right, from Zn onto Zn. So we map f onto the image of the class of 1 under f, right? As I just said previously a few minutes back, that if f is an automorphism, it should take a generator onto a generator, right? That you know. So if 1 is a generator in particular, and if you apply the automorphism f on 1, then f should map 1 onto a generator of Zn, right? And what are the generators of Zn? Those are precisely the elements of Zn star, right? That is, those are precisely those classes, those congruence classes whose representatives are relatively prime to n, right? Right? Yeah. Yeah. So what I am trying to say is, f of 1 always belongs to Zn cross. Whenever f is an automorphism of Zn, the image of 1 under f is an element of Zn cross, right? That is, it is a particular class which is relatively prime to n, right? So to sort of wrap everything up into a single small statement, what I am trying to say is that Psi is a well-defined map. This map Psi that we have defined, it's a well-defined mapping of odd Zn into Zn cross, right? This is what I am trying to say. So I leave it to you to check that. So check that. So check that Psi is a homomorphism, but that's not enough, right? You also need to prove that it's an isomorphism, right? So in other words, you need to prove that the map is bijective. Now here I would mention a small trick that you often do, which is observe that the set on that is the domain of this map, odd Zn, and the codomain Zn cross, both are finite, right? Both are finite sets in particular, right? And both have the same cardinality. So if you want to show that a map Psi is bijective, it is just enough to show that the map Psi is injective, or it is enough to show that the map is surjective. Because if it is injective, then it automatically becomes surjective by the pigeonhole principle, right? You can just run an argument in your mind, and yeah. So the point is, you just need to show that Psi is injective or Psi is surjective, right? So Psi is clearly injective, right? So after you prove that it's a homomorphism, to show that Psi is injective, you just need to show that the kernel of Psi is trivial, right? Consists of only the element, only the identity element, right? So let f belong to kernel of Psi, that is, let f be an automorphism of Zn that belongs to the kernel of Psi. Then we know that Psi of f psi of f, which we have defined to be f of 1, right? This has to be equal to what? Psi, since f is in the kernel, this has to be equal to 1, right? Which is the identity element of Zn cross. So f of 1 is 1, and since f is an automorphism of the additive group, so what we clearly know is that f of any k is equal to f of k times 1, which is equal to k times f of 1, which is equal to k, right, for all k in Zn, for all k in Zn. Yeah, the point is, if f is in the kernel, then f is the identity map, so which implies f is the identity automorphism. In other words, what we have proved is psi is therefore injective. And hence psi is an isomorphism. By the argument that I said, that if you have an injection between sets which have the same cardinality, then it's also it's in fact a bijection, right? So in other words, what we have basically proved is this fact that automorphisms of Zn is isomorphic to Zn star, right? The group of automorphisms of Zn is isomorphic to Zn star. Now in the same spirit, you can ask the question, what is, see, you know Zn is a cyclic group, it's the cyclic group of order n up to isomorphism, right? Similarly, Z is the infinite cyclic group, right? Up to isomorphism, it's the only infinite cyclic group. So you can ask the same question, what is aught Z? And the answer to this will again be very simple. It will follow by the same trick, that you just keep this in mind, that automorphisms of a group always map they always preserve orders, right? In not only do they preserve orders, they will always map generators onto generators, right? So you look at this particular fact, that what is what is aught of, you just find out what are the generators of Z, right? You know that the Z is an infinite cyclic group, and Z has two generators. You can either generate Z fully by 1, or you can generate Z fully by -1, right? So if phi is an automorphism of Z, that is, in other words, if phi is a bijective homomorphism of Z onto Z, then you know that phi should take 1 to either 1 or -1, right? So if phi takes 1 to 1, you just get the identity automorphism, and if phi takes 1 to -1, you just get this particular automorphism. So you have two automorphisms. Since I don't have much space, I will write it here. So there are two automorphisms, one which maps A onto, okay, so one which maps n onto n, and the other one which maps n onto -n, right? So in other words, two automorphisms. So there are exactly two automorphisms of the infinite cyclic group Z, right? And since there are two automorphisms, you know that the group aught Z of all automorphisms of Z has order 2, right? And you know there is only one group of order 2, which is Z2. So so the group is Z2. Yeah. So aught Zn is Zn star, that we have proved, and at the same time we have also proved that aught of Z is Z2, right? Yeah. So yeah, maybe the writing here is not bit clear, because we have sort of answered the second question right. I mean, it's a bit clumsy. I'll make sure I'll sort things out after the class. Okay. So do you have any questions for the time being? If you don't have questions, then also reply something, maybe no or something, because I am unable to understand if you are able to hear me and understand me properly. Can anyone reply? Yeah. Okay. So you don't have questions, and I hope it's the same for all of you. If you have, just unmute and ask. So now we talk about a very simple problem. This is something that you have learned this particular week, which is the notion of the direct product of two groups, right? So you are given two groups, and what you do is you combine them to form a larger group. But there are various ways of doing that. You have studied two particular ways. One is the direct product and one is the semi-direct product. We are here talking about the direct product. So this is a question that suppose G is a group and suppose that N is a normal subgroup of G, then the question asks whether G is isomorphic to N cross G mod N, right? You know that N is a normal subgroup of G, so in particular you can take a quotient, right, of G over N, I mean G by N. So this question asks you whether G as a group is isomorphic to the direct product group N cross G mod N or not. This is the question. So does anyone want to answer? So is this statement true or is this false? G is a group, N is a normal subgroup. So this statement is true. Okay. So maybe Ravi, you can just unmute and let me know why you are saying this. Why this is true? If you don't want to speak, you can just write down in the chat also if you have a reason that this will be true.
This is true due to because of G upon N. N is the normal subgroup of G.
Okay.
And G. So N. G upon N. This is also N cross.
Okay, so if you guys, anyone else wants to try this, that G whether G will be isomorphic to N cross G mod N or not? I mean, it's very tempting to say that it will be true, but it is actually false. Unfortunately, it's false, and a simple counter to this is this one. So you take, so this will be false. So take G to be equal to Z4 under addition, which is the cyclic group of order 4, and what you do is you take the normal subgroup N to be equal to the class of 0 and the class of 2. It's a subgroup of Z4 of order 2, and not only so, it's a normal subgroup because G is abelian, right? So any subgroup will be normal. So in particular N is normal. So what is G mod N? G mod N has order of G over order of N, which is 4 over 2, right, which is 2, which implies that G mod N is a group of order 2, and the only group of order 2 is, so G mod N is isomorphic to Z2, right? Yeah, and also N is isomorphic to Z2. So N cross G mod N, this is isomorphic to Z2 cross Z2, right? This is true. N cross G mod N is isomorphic to Z2 cross Z2. Now, is this isomorphic to G, which is Z4? Is it the case that Z2 cross Z2 and Z4 are isomorphic groups? Both are groups of order 4, but are they isomorphic? Z2 cross Z2 is the claim 4 group that you know, and Z4 is the cyclic group of order 4. Are they isomorphic? No, right? They can't be isomorphic, right? Yeah. Yes?
The 4 order element, there is no 4 order element.
Yes. Good. So, so is this, instead of writing is this, I should write this is not isomorphic to Z4. Yeah. So this is a counter example, right? So even if this is very tempting that you say that yeah, the statement is true, but yeah, it's actually false. It's not the case. So later maybe I don't know, maybe you'll study about short exact sequences of groups and split short exact sequences and all that, and these kind of problems will be considered in greater detail in such situations. For now, you just know that this is not a true statement. Okay. So we now come to the next question. This is a bit this is bit of huge as a question, but yeah, nevertheless the idea is very important, and this is something that you can use later many times whenever, let's say, you are talking about, so whenever you are trying to solve problems on silo theorems and all that. So just keep this in mind, that suppose that G is a finite group and you take a proper subgroup of G which has finite index, that is the number of cosets of H in G is finite, left cosets, let's say, yeah, and you also have this condition that the order of G doesn't divide the index of H in G factorial, that is order of G doesn't divide G is to H factorial. Okay, so order of G doesn't divide the index factorial, so you are asked to show that G has a non-trivial proper normal subgroup. Non-trivial proper normal subgroup. So what you mean by this is, it's a non-trivial normal subgroup, it's not the identity subgroup, and it's also proper. So you have to find a normal subgroup other than the identity subgroup and the entire group. That is what you are asked to find. So does anyone have any idea how to do this? I know that you have learned group actions this particular week, right? So we will try to attack this problem using group actions. So whenever you have some condition like this, that the order of G doesn't divide the index of H in G's factorial, that means that okay, fine. So first so assume that the index of H in G is equal to n, right? So can you give me an example of a group which has order n factorial, a very popular group which has order n factorial?
Symmetric group.
The symmetric group, right? Yes, the symmetric group. So it's Sn, right? And whenever Sn comes into the picture, you be very sure that you have to, since you also have this condition that the order of G doesn't divide n factorial and all that, this is a sort of a very this is an indication of the fact that there are some homomorphisms involved, or there is some kind of group action involved in the picture. Okay, so so we'll make G act on something. What is that something? That something will be the left cosets of H in G. So we'll make G act on the left cosets of H in G, on the set of our left cosets of H in G. You know that this set on which G acts, this has order n, right? That you fully understand. This has order n, since the index of H in G has been assumed to be n. So if G acts on this, you know that every action gives rise to a permutation representation or a homomorphism from G from G into the symmetric group on the set on which G acts, right? So here G acts on a set with n elements, so you get a homomorphism from G into Sn, right? Yeah. And we are getting closer to what we want to achieve. So G acts on left cosets of H in G as, so what is the action? So you take a group element, it hits some coset AH and moves it to GAH, okay, for all G in G and AH in this set. Yeah. So you just check that this is an action. So you check that this is a group action. You know what are the axioms of a group action. Whenever a group acts on a set, it should act nicely, right? That is, a group structure should be reflected in the action. So you just check that this is a group action of G on the set of our left cosets of H in G, right? So just a moment. Yeah. So this is an action, and this induces a group map or a group homomorphism, right? This you know, you have studied group actions this week. So this induces a group homomorphism, let's say phi from G to S, Sn I will write, okay, that is the symmetric group on the set of all left cosets of H in G, and since there are exactly n left cosets of H in G, this symmetric group is the same as Sn, right? So this induces a group homomorphism phi from G into Sn, right? So far so good. What we want to find out is a proper non-trivial normal subgroup, right? That is what we want to find. Okay, so just to make things clear, I just instead write it as S omega, where this is omega, the set of all left cosets of H in G. I'm calling it omega, and I'll just take S omega. So now it's very clear that phi is a you get a homomorphism, group homomorphism phi from G into S omega, right? Which is a symmetric group on the set omega of all left cosets of H in G. And we want to find a non-trivial proper normal subgroup. Firstly, you know what normal subgroups are, and you know that normal subgroups of a group are precisely kernels of homomorphisms, right? They are precisely kernels of group maps or kernels of group homomorphisms, right? So we can in particular look at the kernel of this particular group homomorphism that we have obtained. So consider the kernel of phi. Okay, this is a normal subgroup of G that you know. Kernel of phi is clearly a normal subgroup of G. So even if we have found out a normal subgroup of G, we need to make sure of two things, right? Firstly, as the problem says, you have to find out a non-trivial proper normal subgroup, right? So you have to find out a non-trivial subgroup, and moreover it must be proper. So there is no guarantee as of yet that the kernel of phi will be a proper subgroup, right? It is a normal subgroup, but there is no guarantee it will be a proper subgroup or a non-trivial subgroup. So observe that if G is in the kernel of phi, then what this means is that phi of G is the identity map, right? From omega onto omega, right? Which means that phi of G is the identity permutation on omega. It fixes every element of omega, right? So in particular, it should fix the coset H, right? H is also an element of omega. So in particular, it should also fix H, which implies that phi of G of H is equal to H. Okay, let me just to make it clear, I am writing EH here, the coset containing the identity. So phi of G is EH, and what is the definition of the map phi, the group homomorphism of the permutation representation? It is precisely the map induced by the action, right? So phi of G of EH precisely means G dot EH, right? So G dot EH is EH, which basically means, as by our definition of an action here, this means that GH is EH, which in other words means that G is in H. So what we have basically proved is that if we take an element G in the kernel, then G actually belongs to H, right? Which implies that the kernel of phi is contained in H, right? Now recall what H was initially. H was taken to be a proper subgroup of G, right? And if the kernel of phi is contained in H, then the kernel of phi is also a proper subgroup. So we have at least found out a normal subgroup which is proper. That we have found out. Now the question is whether it is trivial or non-trivial. So does anyone want to answer whether this particular subgroup, the kernel of this map phi, it's a proper normal subgroup, whether this is trivial or non-trivial? I claim that it will be non-trivial. So why should it be non-trivial? Does anyone want to answer? You can just reply in the chat as you were doing previously. Anyone wants to answer? I'm audible, right? So maybe you can reply in the chat if you don't want to answer as well. Unless you interact, I won't be able to understand. Or you can unmute yourselves and then also you can answer. So does anyone want to answer? So note that we haven't used something in particular, right? We have used everything, we just haven't used this particular condition. We still haven't used this, right? So the question here is basically to find out whether the kernel of phi is trivial or non-trivial, right? Now what would happen if it were trivial? Okay, so if kernel of phi is trivial, what does that mean? Then phi is injective, right? And what happens if the map phi from G into S omega is injective? In that situation, G, this map phi will be an isomorphism of G onto its image, right? Right? So what I am trying to say is that G can be embedded into S omega as a subgroup, right? And you know, you have already studied by Lagrange's theorem that if G is a finite group, and if you take a subgroup of G, which if you take any subgroup of G, then the order of the subgroup must divide the order of the group, right? Simple as that. So by Lagrange's theorem, order of G will divide the order of S omega. What is the order of S omega? As we noted previously, this is precisely G is to H factorial, right? This is a contradiction. And then you are done. This kernel of phi is the required subgroup. It's a normal subgroup, it was proper as we proved, and it is certainly non-trivial. If it were trivial, then you would get this contradiction, right? So is it okay? Do you have any questions? Do you have any questions? Just feel free to talk. It's completely all right. If you have any questions, just ask. If you don't have, then also let me know. Respond at least. You have any questions? Did you understand it fully? I'm audible, right? Hello?
Yes, sir.
Yeah. So you have any questions, or is it okay?
No, sir.
Okay.
Up to this, no, sir.
Okay, good. So just keep whatever this particular statement in mind, because we'll use this kind of statement. This kind of theory. This is rather a theorem. Maybe it's called the index theorem or something. I don't remember exactly, but yeah, we are going to use it sometimes whenever we'll let's say in the later classes, whenever we'll be talking about silo subgroups and all that, we are going to use this. And so it's very important that you keep this in mind, the proof and all that. It's a very simple thing. You just use the basic idea of group actions, and that's it. Okay. So now we come to question 5. This is again more related to your assignment. Sort of, it is. Some questions are there from your assignment and all that. But yeah, okay. So let's just look at this question. So you are asked to find out which of the following statements are correct. Right? So question 5, which of the following statements are correct? So statement A is that Z is isomorphic to Z cross Z. B is Q is isomorphic to Q cross Q. Statement C is D10 is isomorphic to Z5 cross Z4. And statement D is there will exist an element in D9. D9 means the dihedral group whose conjugacy class has order 10. So what do you think? Which of the following statements are correct? So first of all, let's look at statement D. You studied dihedral groups this particular week, right? So what do you think? Does there exist an element in D9 whose conjugacy class has order 10? You know what conjugacy class is, right? And you also know that what is the order of the conjugacy class of an element, right? So you know that if A is in a group G, okay, I won't write so much. If A is an element in your group, you know that the order of the conjugacy class of A will be the order of the group over, that is divided by the order of the normalizer of the element, right? So order of CA is equal to order of this is equal to order of G over order of NA, right? This you know. And if I probably think you know, right, because you have studied conjugacy classes, and if you don't, then you can just prove it using group actions. You can make the group G act on itself by conjugation, and you can use the orbit stabilizer theorem after that. As simple as that. So order of the conjugacy class of A is order of G over order of NA, right? That you know. Now how many elements does D9 have? What is the order of the group D9? That you can answer, right, easily. So anyone in the chat? How many elements does D9 have? Dihedral group. The symmetries of the 9 gone. How many elements are there in D9? Someone? How many?
Order of D9 is equal to 2 and 18.
Yes, it's 18, right? So the question, the option D says that whether there exists an element in D9 whose conjugacy class has order 10. Does there exist an element in D9 whose conjugacy class has order 10? So what do you think? Is it true or false? What do you think?
Really, sir, I forgot how can calculate the conjugacy class. That's why I didn't.
Oh, how to calculate the conjugacy class, or how to calculate the order of the conjugacy class?
Sir, how to calculate the conjugacy class?
Yeah, conjugacy class, as you know, is basically this, right? If A is an element in your group, then the conjugacy class of A is defined to be G A G inverse, right? Says that G is in G, right? And this has ordered precisely the order of G over the order of the normalizer of A. That is, normalizer of A, by the way, is the set of all elements, as you know, which commute with A, right? So my point is not the fact. So what I mean, so what I essentially mean by this expression is, so this implies that cardinality of conjugacy class of A times the cardinality of normalizer of A is equal to the cardinality of G, right? In other words, the cardinality of the conjugacy class of A divides the cardinality of the order of, divides the cardinality of G, right? So in this case, D9 has 18 elements. So does it have a conjugacy class of order 10? Can it? No, right? Because the order of the conjugacy class will divide the order of the group, which in this case is 18. So 10 will,
10 not divided.
yes, 10 doesn't divide 18. So this cannot be possible. This is completely false. So as 10 doesn't divide 18. Right. Let's come to the third question. So is D10 isomorphic to the product group Z5 cross Z4? Z5 is the cyclic group of order 5, Z4 is the cyclic group of order 4. So is the dihedral group of order 20 isomorphic to this product group? D10 is the group of all isometries of the 10 gone, and it has precisely 20 elements in it. So is D10 isomorphic to Z5 cross Z4? What do you think? Yeah, you can, yeah, what were you saying? No.
This is true.
Okay, this is true. Okay, this is true. So why is this true? Both have, or both groups have order 20, but does this always mean that they will be isomorphic?
Yes, sir, because of D10 have 4
Yeah.
order element and also 5th order of element. That's why.
Yeah, but how does that actually imply that the groups will be isomorphic? D10 can, so let's just look at this example. No, actually, so Z4 and Z2 cross Z2, right? Z4 also has, both these two have the same order, right? And yes, very good. Yes, D.
Because of this, a cyclic is not cyclic.
Yeah, yeah, these are okay. Just yeah, what I'm saying is one has order. I mean, both groups have elements of order 2, but and they have the same cardinality, but they are not isomorphic, right? So that won't be a good argument. Whatever you're saying, or Preeti was saying, I guess. So that Z5 and Z4 are abelian. I mean, sorry, Z5 and Z4 have elements of order 5 and 4, and D10 also has elements of order 5 and 4. Z5 cross Z4 has elements of order 5 and 4, and D10 also has the same. So that's not an argument, right? That doesn't imply that they will be isomorphic. Even if they have the same cardinalities, that doesn't imply they will be isomorphic. So Tamali Tamilasaran. So I'm sorry for mispronouncing it, but yeah, you are totally correct that D10 is not an abelian group, right? While Z5 and Z4, they are abelian, so that their direct product is also abelian. So Z5 cross Z4 is abelian, D10 is non-abelian, so there cannot be an isomorphism. So this is wrong, as D10 is non-abelian. Simple, right? So I was planning to do more questions. I was also going to talk about twofold semi-direct products of Z. This was one question that I had in mind, that is, find all possible semi-direct products of Z with itself. And this was one question that I had in mind, and also conjugacy classes of D4, because you have a question in your assignment to find the number of conjugacy classes of D5, I guess. So yeah, maybe since we don't have much time left, we have only 6 to 7 minutes maybe. So I will just write down these questions. I mean, I'll solve them and I'll just upload them so that you can see them later. But for the time being, let's answer the rest of the two.
Tell me Q cross is isomorphic to Q cross Q.
So you are saying it's correct.
Not correct, but I didn't get the reason.
Okay, you didn't get a reason for this. Okay.
Okay.
Okay, so they are not isomorphic. You are extremely correct. They are not isomorphic, but there's a reason that they are not isomorphic. Why are they not isomorphic? So just check that. So you consider Q cross Q and consider these subgroups. So it has two these are two subgroups of Q cross Q. One is Q cross 0 and one is 0 cross Q, right? And what is their intersection? Let's call it H. Let's call it K. So what is H intersection K? It's the trivial group, right? They have trivial intersection. In other words, Q cross Q has two subgroups which have two non-trivial subgroups which when intersected give you the trivial group, right? My question is can the same be true for Q? So in other words, does Q have two non-trivial subgroups whose intersection is trivial? See, if they were isomorphic, then whatever group theoretic property the first group has, the codomain, that is the second group, will also have the same property. In particular, if Q, let's say Q, you take an isomorphism which might exist from Q cross Q to Q, and you have found out two subgroups in Q cross Q whose intersection is trivial. Then since phi is an isomorphism, right, so it maps the structure fully onto Q, right? It's a bijective map which preserves the structure. So so that would in particular mean that Q will also have two subgroups whose intersection, it will have two non-trivial subgroups whose intersection is trivial. But this is what I am asking. Does Q actually have two non-trivial subgroups whose intersection is trivial? In other words, if A and B are two subgroups of Q which are non-trivial, can it be the case that their intersection is trivial? What do you think? So let's proceed. Let's take A to be a subgroup of Q and B to be a subgroup of Q. which are non-trivial. So A is not the zero subgroup, identity subgroup, and B at the same time is not the zero subgroup or the identity subgroup. What can you say? If A is non-trivial, so there exists an element m over n in A, right? Such that m is non-zero, right? This you know, since A is non-trivial. At the same time, since B is non-trivial, there exists an element P over Q in B such that P is non-zero, right? Now what can you do? What you want to show is that there is some non-trivial element which is in the intersection, which is in both, right? So that the intersection can't be trivial. So m over n is in A, which is a subgroup, so it's in particular closed under addition, implies that m, which is n times m over n, that is m over n added to itself n times, this is also in A, right? Which implies that m added to itself p times, that is mp, is also in A. Similarly, p over q is in B will imply that p, which is q times p over q, this is also in B, which implies that m times p, that is p added to itself m times, is also in B. Thus, A intersection B is non-trivial, not equal to the zero subgroup or the trivial subgroup, right? And that's your reason, as simple as that. If they were isomorphic, Q would also have the same property, that there exist two non-trivial subgroups in Q whose intersection is trivial. But clearly you have proved that if A and B are arbitrary non-trivial subgroups, then their intersection can't be trivial, right? So we have proved. So this is false, and the reason is as given below. And finally, Z and Z cross Z, they are also not isomorphic. This is also false, as this answer is simple, as Z is cyclic, but Z cross Z is not. You can check this, that Z cross Z is not cyclic. It must have at least two generators. That is, in other words, what I mean by generators here is, it must have a set which consists of two elements and which generates Z cross Z. You can check that 1 0 and 0 1 together can generate Z cross Z, but single-handedly, I mean just 1 0 or just 0 1 cannot generate the entire group Z cross Z. In other words, Z cross Z doesn't have a generating set consists of a single element. Or to rephrase it, Z cross Z is not cyclic. You can check this very simply. It's a very simple computation. Okay. So, are there any questions so far? So, I'll solve these problems. I'll write down solutions to them and I'll upload them so that you can see. The number of conjugacy classes of D4 I really wanted to do, but there's no time actually. I don't know. Does the meeting stop automatically? It does, right? Or does it not? Okay, so it might stop. I'll just wait for a few minutes to see if it stops. If it stops, then bye. But if it doesn't, then we will continue. Let's see. So do you have any questions so far? Do you have any questions so far? Anyone wants to answer something maybe? By the way, are you guys master students or BSc students? Are you guys masters or BSc students? Okay. And the rest of you? MSc, good. Okay. So most of you, okay, so you are BSc, okay. Alright. So the meeting hasn't stopped, so I guess it's safe to continue a few more minutes, right? I thought that it stops after an hour. Okay, you're basic. I thought that it stops after an hour, but we can maybe continue a few more minutes with this. Okay, so I'll solve this particular problem, the last one, which is about the number of conjugacy classes of D4. So what do you think? What is the number of conjugacy classes of D4? So you have 4 options here. And by the way, if the meeting stops, then I guess we won't join again. So bye to all of you. But if it doesn't stop, then yeah, we'll continue. I'm sorry for this, but I actually don't know how Google Meet properly works. Because earlier the meeting used to stop after an hour. So anyways, so the number of conjugacy classes of D4, right? So you have 4 options, 4, 6, 5 and 8. What do you think? Which one of them will be correct? First of all, I'll ask you, let me ask you this. Can this option be correct? Option D. Is option D correct? What do you think? That is, can there be 8 conjugacy classes? You know what conjugacy classes are. So let me draw a picture for you. So this is, suppose this is your group G. So there are elements in your group and the conjugacy classes form a partition, right? Because they are precisely the equivalence classes of an equivalence relation on your set or on your group G, right? Conjugacy relation, right? So they form a partition of your group. Now I am asking whether there can be 8 such equivalence classes. The group itself has 8 elements, and if there are 8 equivalence classes, you know that every equivalence class should be a singleton, right? That is, it should contain a single element. Each equivalence class will contain exactly one element. But is that possible? Is that possible? So let's see, what does a conjugacy class having a single element mean? So in other words, let's observe what does C of A equal to the singleton A mean? That is, what does it mean when we say that A is the only conjugate of itself? That means, you know what CA is, right? It's precisely the set of all conjugates of A, right? That is G, A, G inverse, where G varies over the group. So this means that all the conjugates of A are precisely A, which means that GA is equal to AG, right? For all G in G, right? That means if, yes, good, yes, that is what I'm trying to say. Since GA has exactly 8 elements, the conjugacy class of A only consists of A, this means that A commutes with every element of the group, right? Now if every conjugacy class has exactly one element, that means all elements commute with all elements of the group, right? Or in other words, what this means is that the group will be, yeah, sorry?
A belongs to center of G.
Yes, for every A, very good. That means that the group is abelian, but D4 is clearly non-abelian, right? D4 is non-abelian, so this can't be possible. So there cannot be 8 elements for sure. That we can be completely sure of. So this is obviously wrong. Now let's actually compute. Let's actually compute the conjugacy class of D4. So if you recall, D4 was the set of all symmetries of the square, right? And there are exactly 8 such symmetries. And if we were to list the elements, then those were this, right? So D4 is equal to 1 R square, R cube, S R square, S, okay, sorry, S, then you have SR, S R square, S R cube, right? What are R and S? R is a rotation having order 4. So R to the power 4 is identity. This is one relation that you have. S is a reflection, as you know. It has order 2. And you also have this particular relation as was defined in your class when you were studying dihedral groups, that SRS is equal to R inverse, right? Let me check. Right, SRS is equal to R inverse. So later on, maybe right now you haven't studied what presentations of a group is. So later on, you'll be studying free groups and you'll study presentations of a group, and you'll see this, that Dn has a presentation So I'll just say in brief what presentation is, but let me write the presentation actually. So Dn has this presentation: AB such that a to the power n is 1, b to the power 2 is 1, and BAB is equal to A inverse. What I mean by this is Dn is fully generated by these two elements A and B, and what I mean by that also is that every element of Dn is some word consisting of A, B, A inverse and B inverse, right? It's some word, and there are only three relations that you need to keep in mind. A power n is identity, B square is identity, and BAB is equal to A inverse. So with these three relations and with these two generators A and B, you get the full group Dn which has order 2n. So this is a very rough what should I say, rough explanation of what this presentation thing for a group means, but you will learn this later in detail. So we don't need the idea of presentations here to solve this problem. The only thing that we need here is this particular relation that I have written here. Okay. So I'll just maybe I'll just rub it off just to not confuse you. So you have this relation SRS is R inverse, right? So let's now try to find out the conjugacy classes of D4, right? First of all, what is the conjugacy class of the identity element? What is the conjugacy class of 1? Anyone wants to answer? And please answer. What is the conjugacy class of 1? What is the conjugacy class of the identity element in any group? 1 only, right? Yeah. So conjugacy class of 1, C of 1 is equal to 1 because 1 commutes with every element. As simple as that. Now we want to find out the conjugacy classes. So the conjugacy classes will together give you a partition of D4, right? That we know. So we want to find out the conjugacy classes of all the other elements, right? So let's concentrate on R square for the time being, right? So we want to find out what is the conjugacy class of R square. You know, as we just saw previously, that the order of the conjugacy class of any element A is the order of the group divided by the order of the normalizer of that element, right? In particular, the conjugacy class of any element should have some order which divides the order of the group. In this case, the order of the group is 8, right? So the conjugacy class of any element can have either 1 element, 2 elements, 4 elements or 8 elements. Now we clearly saw that the conjugacy class of an element cannot have 8 elements, right? Because if the conjugacy class of one element has 8 elements in it, then that means that the conjugacy class of that element consists of the entire group, right? The conjugacy classes form a partition of the group. So every element has the same conjugacy class consisting of all the elements of the group, right? That is, there is exactly one conjugacy class, but that is impossible, right? So the order of the conjugacy class of A cannot be 8. Oh, sorry. Yeah, I twisted the argument a bit. That's not what I want to say. The conjugacy class of A divides the order of the group, so it can have order exactly 1, 2, 4 or 8. Now the conjugacy class of fine, yeah, you can say, yeah, okay, fine. So fine, let's just compute the conjugacy class of R square. So you know that the conjugacy class of R square can have, so C of R square can be either, I mean cardinality of this can be either 1 or 2 or 4 or 8, right? That's true. So instead of finding the order of the conjugacy class of R square, what we want to find out is the order of the normalizer of R square. So order of in R square, this is what we want to find out. Again, this is a subgroup. I mean, this is a subgroup of the group. So it will have order which divides 8. So it can be 1, 2, 4 or 8, right? So what are the elements which commute with R square? That is, what are the elements which are in the normalizer of R square? Clearly, normalizer of R square certainly contains 1, right? So 1 is in the normalizer. At the same time, R is also in the normalizer because the subgroup generated by R contains R square, and the subgroup generated by R is a cyclic group, it's abelian. So R commutes with every element of that group, or any two elements of that of that subgroup of order 4, cyclic group of order 4 will commute. So R will commute with R square. Similarly, R square will commute with R square, and R cube also commutes with R square, right? So we know that the normalizer has at least 4 elements in it, right? The normalizer of the group has at least 4 elements in it, right? So that means that the order of the normalizer of the element R square, the order of the normalizer of R square must be either 4 or 8, right? Since it has to divide the order of the group 8. So we know that this is 4 or 8, right? So this means that if we can find one more element which commutes with R square or which is in the normalizer of R square, then it will have all elements in it, right? So so can we find one more element? Let's see. So what is S R square? Does S commute with R square, or is S in the normalizer of R square? So S R square, as you know, is R to the power 4 minus 2S, right? You can just use this relation that I have written here. Just use this relation again and again to compute this. Simple. If you have some doubt, I can just compute it by hand. So S R square is SRS, right? Which is SRS na SRR. So this is the same as saying that SR is R inverse S, right? So SRR, and SR is R inverse S, so R inverse SR, right, which is R to the power R inverse S, that is R to the power minus 2S, which is the same as R square S, right? So indeed we see that SR square is R square S. In other words, S commutes with R square, right? That means S is also in NR square. So the normalizer has 5 elements in it, right? And hence normalizer of R square greater than equal to 5, which implies that the normalizer of R square must have order 8, right? Which implies that the cardinality of the conjugacy class of R square is order of G by order of the normalizer, which is 8 over 8, which is 1. That means the conjugacy class of R square consists of one element exactly. So we know C of R square is equal to R square, right? And let's focus on the other elements. So what is the conjugacy class of R? Again we want to find out the normalizer of R. So what is N of R? So N of R is equal to, what are the elements that are in the normalizer of R? So clearly one is in the normalizer of R. Then R itself is in the normalizer, R square is in the normalizer, R cube is in the normalizer, right? So again, as the argument, as we have said before, the normalizer of R consists of at least 4 elements. So it can have either 4 elements or 8 elements, right? Thus N of R must have order 4 or 8, right? So if we can find at least one element which is in the normalizer, one more element other than this 4, then we know that its order has to be 8. And if we can find one element which is not in the normalizer, one more element other than this 4, then that means that the normalizer cannot have order 8. It will have order exactly 4, right? So let's just see what is SR. SR is an element in your dihedral group, this element, right? And what is RS? RS, by the same computation, by using this relation again and again, RS you can check is just SR cube, right? So SR is definitely not equal to RS, right? That means S doesn't commute with R, or S is not in the normalizer of R, right? Thus S doesn't belong to normalizer of R, which implies that, as simple as that, which implies that order of the normalizer of R is exactly 4, which implies that the order of the conjugacy class of R is 8 by 4, which is 2. So there are 2 conjugates, and we know that the conjugacy class of R certainly consists of R. And what is one more element that can there be? So you just take this. Observe that we have already written this, right? SRS is R inverse. This is a relation, right? So we know that SRS is just S R S inverse, since S has order 2. That means we are only considering the conjugate of R by S, the conjugate of R by S. So this is S R S inverse, and this according to a relation is R inverse. So this is R inverse, that is R cube, right? So what this means is that the conjugacy class of R consists of R and R cube. Since there are two elements, these will be precisely the two elements. So up till now we have these conjugacy classes, one, the conjugacy class singleton R square, and this conjugacy class R and R cube, right? So we still have 4 elements left to check, right? So let's focus for the time being on S. So again, what is a normalizer of S? Just observe that since the conjugacy classes form a partition of your group, and already one R, R cube and R square are sitting in conjugacy classes, so the conjugacy class of S should be made up of elements, should be made up of the rest of the 4 elements, right? S, SR, SR square and SR cube. Some of them might be in the conjugacy class of S, some might not be. What I am trying to say is that the conjugacy class of S should have order less than equal to 4. So we know C of S is a subset of S, SR, SR square, SR cube, right? Right? This is a subset of it. So C of S must have order 1, 2 or 4, right? So let's just look at the normalizer of S. What is N of S? N of S contains 1. Clearly we know this. N of S also contains S. S commutes with S. N of S at the same time, as we have found out, observe here, we have written this where, yeah, we have proved that the we have proved that the conjugacy class of R square consists of itself only, right? That is, R square is a single conjugacy class, right? That means that R square commutes with every element. So R square in particular will also commute with S. So this also contains R square, right? So the normalizer of S contains at least 3 elements, right? And we know, so all these 3 elements belong to the normalizer of S, right? Which implies that the cardinality of the normalizer of S should be greater than equal to 4, which implies that the cardinality of the conjugacy class of S should be less than equal to 2, right? The conjugacy class of S should have cardinality less than equal to 2, since the order of the conjugacy class of S is the order of the group over the order of the normalizer of S. So this should be less than equal to 2 clearly. Now the conjugacy class of S consists of S that we know. We just need to find one other element which is not in the conjugacy class. Just recall that even though R square commutes with S, so if you just try to conjugate by R square, you just get S only. So you need to find some element which doesn't commute with S, right? We have already observed that R doesn't commute with S, right? So it's simple. It's enough to find out RS R inverse, right? So what is RS R inverse? We already have a relation, right? So SR is R inverse S, right? So using the relation again and again, simple computation. This gives you S R square. You can simply check this just use that relation again and again and again, and you'll get this. I mean, we can do that. It's not that we can't. So SRS is R inverse, that we know from the relation. So this is RS SRS, right? And SS is S square, which is identity. So this is R square S, right? And this is therefore SR square. We have already proved that R square and S commute, right? So the conjugacy class of S consists of S and SR square. That we have proven. This is logic behind this. And finally we are left with 2 elements. We are left with these 2 elements, SR and SR cube, right? These are the 2 elements left, and you can check that they together form a single conjugacy class. Why? Because just the same argument, right? The conjugacy class, the order of the conjugacy class of SR can have 1 or 2 elements. Either it consists of a singleton or it can have SR cube as well. So you can check this, that the order of the normalizer of SR is exactly 4, right? Why? Because normalizer of SR contains 1, it will contain R square, it will contain SR, right? it will contain one R, it has one R square and SR. So it has at least 3 elements, that means it will have exactly 4 elements, which implies that the conjugacy class of SR has order 2, 8 over 4, which is 2. Thus, and since there are only 2 elements left here, right, thus conjugacy class of SR is equal to SR and SR cube. So you have actually computed rigorously by hand what are the different conjugacy classes. So the answer is 1 is a single conjugacy class, R square, this is a conjugacy class, the class containing R and R cube is a conjugacy class, the class containing S and SR square is a conjugacy class, and finally the class containing SR and SR cube is a conjugacy class. So there are exactly 5 conjugacy classes, okay, and that finishes the problem. So 5 is your answer, okay. So that's it from my side for today. So do you have any questions so far, or is it completely all right, everything's in place? Just maybe you can unmute yourselves and let me know. So are you comfortable with whatever you have done today? Maybe someone, I mean you can reply, there's no problem. Yeah, what were you saying? Is it all right? Okay.
Yes, sir.
Okay, so fine. So we'll wrap it up for today. So in case you have any questions, this is you can always write the questions in the discussion forum, and people will answer that, or you can just email me. You have my email ID here. I've written it, so you can email me if you have any questions in this. Okay, and so let's meet next week. So I'll stop the recording and